So,
Okay, yep.
hello. This is the last lecture of our lecture series, and it couldn't be a more appropriate lecture than yours, Wyly, thinking about the future.
Okay.
I realized that I have my notes on you too far for my eyes to actually see. So, but lucky for me, I also know Wyly. I met Wyly 20 some years ago in grad school. And before that, Wyly had already, had come to the school with a degree in anthropology and a lot of experience in making. So a degree in architecture made a lot of sense, probably. Ever since graduating the Harvard Graduate School of Design, Wyly has been practicing in Germany and in the States, making a lot of cool things. He is currently a professor at Washington University in St. Louis, and I might let him take it from there.
All right.
Okay.
Well, let me see. I need to share my screen. Let me make sure I do this right here. Actually, let me see. It's always whenever you open up PowerPoint, it does this funny. So let me see if I get this right. Okay, let me try that. Sorry. There we go. Can you, which scene, do you see my proper screen or like my split screen?
You see your split screen.
Okay, let me undo that. Let me try that again. Is that better?
Perfect.
Okay.
Yes.
All right. Well, welcome everybody. I see you very small on my screen here, but that's okay. My name is Wyly Brown, as Tanya just introduced me. So it's interesting. I mean, we were having some conversations about this project in the spring, and Tanya had asked if I could, kind of reflect on the idea of where we're at with timber today and what the future could hold with timber as a kind of, thinking about the kind of research you guys are doing and work you're putting into looking at the history of timber and how that actually might be a means of promoting or pushing innovation forward in the towards new ways of thinking about timber. So I'm a practicing she said I'm a professor. I'm also a practicing architect. Here's my team in Germany. I have an office that I started there back in 2013 with two partners, Andreas Leupold and Christian Goldbach. We make El Bego Architects. And I run the US office, which is kind of funny. You probably recognize Justin here. He was hanging out with you guys the last couple of weeks. I think he's back in Boston now. This is actually a picture from my Boston office, which I've just closed down and now moving to St. Louis. But so we have this international office of doing all sorts of work, both in the US and in Europe. We don't specialize in anything, but we work to improve the built world by developing practical yet innovative architectural solutions. And so our design process is really based off extensive analysis and exploration of given conditions. And so we've done things all the way from stadiums to youth centers to restaurants to museums to a wide range of things that we work on in Europe and in the US. And so what I like to do in the beginning of lectures, I kind of show a couple topics to demonstrate the breadth of kind of what we do, to give you a taste of it and maybe a little teaser for Tanya to invite me for another lecture. But one of the things I give lectures on is like designing by combining landscape and interior, flowing inside and outside. This is a supermarket that we designed in Germany, almost a completely passively cooled. It's integrated into the landscape and it's made out of a lot of local materials. But the funny thing about the teaser is I'm not actually going to talk about that because I have another topic. Another thing we do a lot of and I talk about is modular construction. So these are some little restaurant pods for the Expo Center in Munich that were designed to be placed in the courtyards to with fully installed kitchens and they're kind of like food trucks, but permanently placed, but they're made modularly and placed over. And this is the first round. And we were about to start a second round, but then COVID hit. So that's been held off. But so it's, innovative construction methods. In the US, I give several lectures about sustainable and affordable housing. I've won a couple of competitions for this topic, but it's something that I'm actually fairly passionate about, which is what I do a lot of my research on here at St. Louis, is how to create better quality of living, but with very low energy use and making it affordable. And another one you might recognize, let's see, I think right here, if Olivia is still there, this is Olivia. I think she might be joining you guys, or she was helping out for a while. This is another thing I do is I address urban vacancies. This is a project that I worked on with Mass College of Art students to build a greenhouse in a vacant lot in the city of Boston. So a range of topics. Again, these are just kind of teasers to throw at you of different things that I work on and I think about, and you'll see that kind of tie into the lecture later on. But the topic for today is timber yesterday, today, and tomorrow. And so where I want to start is actually, it's going to be kind of funny because you guys know this project quite well. And I've been following your Facebook feed from Hans House. Yeah, just to be, as Tanya kind of alluded to, you probably noticed my last name, and you've noticed there's some people on the project the same last name. And so, yes, I am related to them and have been involved with Hans House for decades and been on several of these projects. And what I love about the idea of looking into historical construction methods is it's not only a means of preserving knowledge that could potentially be lost or be on its way of going out. It's a way of really re-exploring the way we do things today by looking at the kind of decisions and the decision-making and the processes that were done before. So particularly when you're looking at something like Notre Dame, and we're in a state today of things like, how do we lower energy use and petroleum products and lower our carbon footprint? Well, what's a better way to do that on a construction site than using an axe and a saw rather than a chainsaw or electric powered saw, or so it's actually using human power and hand tools, dramatically reducing the carbon footprint. And we also start to think about this triumvirate, or this three-legged stool of technique, tool, and material. And you start to think about how were decisions made in the time period that Notre Dame was being built? Why is that using that material? Why are you using that type of joinery? Why are you using those tools? Why not something else? Why not something else? Is this something that could be repeated today other than in this thing? Probably not. I mean, it's probably not an efficient way to do it. I mean, I think, one of the main issues is the lack of huge old growth forests, but it's something we can definitely look back at and think about where people were thinking back then through emulating that process to think about what are the conditions today that we might change or maneuver based off tradition or based off old skills and knowledge and tools. And another amazing thing about it, again, I'm just stealing Hans House Facebook shots, is on projects like this, is that interaction and that communication and community. That actually a design project in architecture school, we always think about like these forms and these spaces, but what's wonderful about a building project, particularly going back in time and looking at another age, is really that community that's created, that bond of going through the process. And so this is, I know I'm telling you things you already know because this is what you guys are in the middle of, but I think it's an important basis for really thinking about how to go forward, is in fact looking backwards. I remember there's all these sound bites of like, you can't look forward, you can't move forward by looking backwards, but I completely disagree. I think one of the best ways to move forward is to first start by looking backwards. So let's look at timber yesterday. And I'm going to look at it on a kind of small scale to start with, and I'll very quickly get to larger scale. And I should actually, Tanya, how long am I set for this lecture? Because I can make it really long or really short, or what's the kind of anticipated timeline? Oh, okay, I can't hear you, but.
This isn't that high. We're slotted for an hour, but.
Okay. No, I can make that work. I'll just have to talk a little quicker and not so be so verbose. So this is looking at actually an Arctic sled called an Accio. And this is the climate that it is adapted to. And the design and construction of this particular timber sledge, that this is something I researched, decades ago, is based off the available materials there. So you have this kind of curved runner here that's that's designed from trees that were grown in a prevailing wind at a particular location in northern Finland, and they're grown bent. And so the tree comes with an already pre-bent shape that's used to make this runner shape. And then there are these planks that are taken from green, freshly cut birch trees that are then steam bent around to make these planks. And of course, the ribs are also steam bent to create the form. So the form and the materials that are available are key in creating a form and a tool that performs in a pretty extreme environment. And so there's this balance between the tools available, the materials available, and the environment that they're based around. So now let's jump up to timber today. Now, I'm chronologically for myself, I actually built these before this sled, but in a sense of really designing with timber for performance on a small scale, I was looking at whitewater paddles. And the way we can look at specific wood species or timber species for their performative aspects in order to optimize a performative instrument. And so we have the shaft here, which needs to have some sort of structural bending element, which is made of a spruce core because it's light with long longitudinal grains, and it has red oak kind of let's say like an I-beam, a red oak. What would you call it, on the upper flanges that take the compression and the tension. So it becomes lightweight, but you use the denser material where you're actually taking the higher loads. And then the blade, which is often in the water, is made out of red and white cedar, which has high water resistance. And it's okay, and because it's today, it's reinforced with some fiberglass and coated in epoxy. And then the edge is coated, or you see this edge that's bent around, because wood can be very flexible when it gets thinner, is made out of maple and mahogany, which are very hard for impact species. So you have this kind of optimized form that has this shaft, blade, and edge, and each element is designed using this particular properties of particular timber species to optimize the performance. Okay, so now let's jump up to a whole nother scale of timber today. This is a place. It's a speed skating stadium that is designed for southern Germany. This is one of the very first large scale projects I worked on back when I was working at Danish architects. And there's this town called Insel, Germany. It's an alpine town where they have this long history of speed skating. And this is kind of doing a they've a lot of people have grown up here and gone on to be Olympic gold medalists or gold medalists in the speed skating World Cups. And so they have this long tradition of speed skating. And and they have this open stadium that they've had for a number of years. But the issue became in around 2005, the rules of international speed skating changed that because the difference between the first place winner, the gold medalist, and the fifth place was often within 1/100th of a second. Sometimes within, between first and third place was within the thousandth of a second. And so if you have an open air stadium like this, you're only racing two skaters at the same time. So you'll have some skaters will go in the morning and some skaters will go in the afternoon. And if you suddenly have a prevailing wind shift, it gives one skater, depending on the wind, which way the wind's blowing, an advantage, and the other a disadvantage. So that the rules change to require a roof and climatized track in order to continue to maintain world-class competitions. And so Insel had this kind of choice they had to make, where they said, okay, do we want to just have this become something that falls into history and we can keep training people here, but really at a low kind of amateur level, because when they get a professional level, they need to be inside to train for the proper conditions? Or do we want to build a new stadium? Well, they decided to build a new stadium and turn this whole area into a huge sport kind of a center for people to come worldwide to train in many different sports. And here's the mayor of Insel at the time. And this outfit kind of seems humorous, but this is actually his dress of when he goes to formal dress in Bavaria. And he had two requirements for this stadium. And one of them was that he wanted to have the fastest ice in the world. And the other one was to have low maintenance costs. And what we discovered very quickly when we deal with speed skating stadiums is that for the most part, speed skating stadiums, there were at the time 11 world-class stadiums with roofs, and we were the 12th, but it was falling out of that designation. Is that they typically find themselves kind of near the train tracks or in kind of an industrial area or not so nice area of town. They're formally, okay, sometimes a little interesting with some structural things because they're huge wide spans, but for the most part, they're just closed boxes that have no access to daylight. And when you're in them, you don't know if it's raining outside, if it's snowing outside, if it's daytime, if it's nighttime. There's one exception of this Chinese one in Harbin, China, that has this huge window that gets very high contrast, so it's even hard to see. But you're basically spending your day, if you're a speed skater, under artificial light, which is a huge maintenance expense or operating expense, or the lights, because you have this 25,000 square foot warehouse essentially that needs to be lit, highly lit, so you can see what you're doing. So we came up with this kind of idea. We said, at the same time, we have this beautiful, you see down here on the right, this beautiful scenery. And to block out that scenery would be kind of horrible. I mean, you really want to, see where you're at, look at the beautiful mountains while you're skating or while you're training or while you're watching somebody else skate, and still maintain this connection between inside and outside while also radically trying to fulfill those technical requirements. So we came up with what we call, I like to call the dumb diagram, the nicer name for it, the schematic diagram, where basically we were going to build this kind of, globulous cloud that sits over this kind of continuous landscape that becomes the track and the stands, and really maintain this connection with the lake and the view of the local mountains while allowing daylight to filter its way into the stadium. And so, this was even before we thought about materials or thought about structure. This was just like, these are the concepts we want to work with. And how do we start to implement that? And so the first thing we did was, okay, well, we have a span of, I think it's close to, it's like 280 or 270 linear feet. So we're talking like bridge scale. So we really needed to focus on structural system. And there was a desire not to have any columns in the middle. So, we started exploring different structural systems, which have, of course, tied themselves to materials at some point. And we landed on the fact that we said, okay, let's just go with a simple single span truss. And you were right in the middle of Alpine Bavaria. And so the other question became really, how much steel are we going to use and how much wood are we capable of using? Can we even span something like this in wood, which is a locally available material? And what type of formal possibilities does that give us? At this point, we were still mainly exploring, on a pragmatic financial basis and constructability, because we had a really tight schedule, but it was something that was in the back of our minds the entire time. And so initially we're thinking, okay, we'll do a very lightweight filigrane roof with lots of steel bits, maybe a few wood elements, and we'll allow the light to filter through. Well, we immediately realized that was technically highly difficult with the amount of snow loads we were going to get. We're going to get like 6 to 8 feet of snow on top of this entire roof for a good part of the season. And just the year before, a ice skating stadium a few miles down the road had collapsed, and it was a wood structure stadium. And so the engineering requirements had suddenly been well elevated to a much higher level of safety zone. So we had to contend with these new rules that were coming out. So we started thinking, oh, what if we use some of these kind of ETFE foil membrane lights to allow light in right over the track and maybe down the middle a little bit. And we were exploring, well, what if we did north-facing kind of sheds or lights that allowed diffuse light only in? And that's kind of where we started landing, is that technically possible or the most technically possible were these kind of north sheds. And so we, in order to test this, we did some daylight simulations to see how much light was getting in. And we saw that, at certain sides of it, we could get enough light, but in the middle, we needed a bit more light. So we had to start adjusting the shape and sizes of these openings to optimize the daylight. But at the same time, we had an issue of we weren't able to allow any direct light from going through these skylights and hitting the track. So we created this kind of, which is now actually pretty standard in Rhino, if you guys are familiar with that, a means of evaluating day by day, hour by hour, where the sun position was and if light would touch the track. And the reason daylight can't touch the ice is because it makes it soft at that point. And if it's soft, that means it's slow. And if it's, depending on the angle of the sun, it also means that you might have hard ice where there's no daylight hitting it, and then very soft ice, which would be very similar to like when you're rollerblading and you suddenly hit gravel. It could actually be dangerous. It could have people trip and fall because it's that much slower than where they're getting speed. So we had to kind of find a way to find the impossible mean between two conditions of maximizing daylight, but minimizing or eliminating direct light onto the track. So we created a complex kind of, let's say, a dynamic grasshopper script that allowed us to change things very quickly, simulate what the results would be, and come to a conclusion iteratively using digital technology. So we created a script that would allow us to take these sheds and move them around, change the size of the openings with just basic sliders, change the angles, and play with what was the optimal location, running it through, seeing if any daylight hit the track, seeing simulating how much daylight was going in, if it was sufficient. And we very quickly, through this iteration and these simulations, in concert with Transolar, which is a climate engineering, and some structural engineers, we realized those middle sheds were not going to work. So we split them. We tried to make that. We realized we needed enough light, so we made these sheds much bigger. And then we saw that as we start making these sheds bigger, that snow is going to build up and start sliding against these skylights, which would cause major pressure. So we wrote another little script to show the direction that snow would slide on these sheds. So all these blue lines are the direction that snow would slide. So here, snow would slide down here and be harmless. But any snow that built up here would slide down here and hit that skylight. So we had to take that into account. So we continued using these simulations and reworking the form. We flipped them around. We halved them, but made them larger. We did some shifting to allow for getting some snow into the later and getting some skating later in the season. And then when we came up to a form that worked, boom, we rendered it. We explained it to the client. We had the engineer pre-check it, and we came up with this form that would work technically. The question came, of course, well, how do you actually build a form like this? What's the best material to get these complex curves and get this form, this geometry? And so we did a couple experiments where we kind of looked at, well, how would you build this out of metal or steel? And how would you get those curves? And what's interesting about steel is very good at making straight lines, but as soon as you do large curves, you have to cut the curved web for a I-beam out of a much larger piece of steel. So you're using huge amounts of material that produces waste that will be recycled, but you're still transporting, creating, extruding this huge amounts of material, and you're welding a lot of custom beams. Whereas when we look back at how to use wood, I was like, hey, well, what about that paddle I did? Well, it's basically the same idea. We've got three elements. We've got kind of a roof, which is kind of standardized. We've got this edge condition that's bent around it. And then we have these skylights that are formed and curved. It's basically a really big paddle. It's just timber, and you pick the species and you pick the construction method to match the specific local need. And we drew it up. And so here's an actual, this is the bid document for the roof. And I think it's a little too hard to see on the screen here, but every one of those joists, which are straight line, every one of these joists here are actually straight lines. The only curved elements are these front pieces, and then the ones that go around the edge is here. So you can actually count the number of joists, and each one of these kind of shed roofs is designed and created individually where it's located and its exact shape and requirements. And we discovered that, actually creating curved wood elements at this scale is pretty much just as easy as creating straight wood elements, because what you're doing is you're cutting it up into little pieces, which I'll get to in a second, and you're gluing it together. And so here's that edge here, this edge condition we see down here, that this is, kind of floating around the edge. And we can create this curved system by, again, using timber technology, cross-laminated timber, CLT, which is essentially like large pieces of plywood, which I'll show in a minute, and create custom forms. So here's a picture of this enormous wooden truss. This is about 30 feet tall in the middle. And 30 feet tall, I mean the truss from the bottom cord to the upper cord is 30 feet. So you'll see that in a moment. But we were able to make these curved wooden beams fairly simply, and mostly with materials that came from within a few hundred kilometers. So the materials came from within a few hundred kilometers. They were processed less than 80 kilometers from the site, and they were delivered. Everything locally produced. So basically, you cut wood down into these strips, you glue them up, and you can, as I said, you can glue them in a straight line almost as easily as a curved line, and then you glue those blocks together. So it's just a matter of taking things, I mean, here's actually a model of something similar, just on a smaller scale model level. You can just very easily make curved pieces of wood by cutting them into thin strips, curving them, clamping them, and now you have fixed curved structural elements. Clamp it all together and then install it on site. So you start to see the scale of what's going on here. It's just little curved, creating curved elements from straight pieces by scaling them down to a point where you can bend them fairly easily and put them back together. So again, here's this edge condition, which it's a compound curve where it curves not only in this direction, but it curves sometimes up and down in the linear direction. And that's created by just taking CLT, cross-laminated timber, and cutting it like plywood and creating these profiles that are then stacked. Then, wooden elements are spanned between, and then take a flexible, thin sheet of plywood, form it around, and suddenly you have, a whole series of these kind of barrel-shaped wooden structures that are of, basically they're compound curves, all made very simply, very cheaply, very quickly out of wood. Here's the stadium coming together. And, here's it under snow, a couple other views with the skylights, the interior. Because of the fact that it's made out of wood, we weren't allowed to leave it exposed because the ice would radiate cold and cause condensation to build up on the wood. So unfortunately, we had to cover the structure in this low emissivity membrane. And here was the World Cup in 2011, I believe. But so we were able to actually create this very complex form using the properties of timber and in a very sustainable way, gathering timber from all within a couple kilometers. So and then it became this kind of iconic building along with their church. I mean, this is the town. There are two main things. A town of 3,500 people had their church was one of the key symbolic things, particularly that steeple, and their speed skating, and then the mountains. So this is actually the view you get as you enter that village from the highway to arrive to any event you're gonna have there. And so it's really looking at, it's using timber technology today. You have the cross-laminated timber and glue-land timber, which allows you to have a wide variety of forms. It's incredibly structurally stable, and it's fairly simple and relatively inexpensive to build that way. So this is a lot of the opportunities that wood provides today. It can be used for all sorts of different types of constructions, and there's also particularly cross-laminated timber is going into creating modular construction and all different types of range of things that are coming out of it. But what I want to kind of throw at you now is looking at timber tomorrow. And this is where I'm going to kind of roll back to that idea of looking at history or looking at indigenous technologies as a means of innovating and thinking about how to solve problems today. So here, and I'm going to jump scale a bit here because, of course, much smaller than the stadium. Here's home construction in the late 1800s. Basically, it's balloon framing in the U.S. And you have this kind of vision of there's some forest nearby that wood was cut down, and I mean you guys are kind of going through this right now. It's milled into these long linear elements. You create a multi-story house. And you're doing it mostly with hand tools and local labor. Well, here's home construction today, which kind of strangely enough, when we're talking about timber construction, looks remarkably similar to what we just saw from over 100 years ago. And in fact, this building that I'm showing you is a building I designed, which is a LEED Platinum, won in a competition for innovation for, it's actually a energy positive, affordable house in the Boston area. And basically the same means of construction. You have some local labor walking around with some sticks that, and putting it together on site. And it begs the question, we are still basically building houses the same way we did 100 years ago in terms of timber. And it's based off that kind of still that romantic idea of cutting down some trees, having a local sawmill, and putting it together with local labor. And in a lot of ways, it's very similar to, building like this, in my mind, is very similar to thinking about, like, this is how we used to build cars about 100 years ago. And if I was like commuting and this kind of thing, you might think I'm some like old eccentric dude, but you wouldn't think I'm being very innovative, or I'm like, really using the technology of the day to do the most energy efficient thing possible. Or if I was, toting around with this phone from 100 years ago, you would, how do I post something on Facebook with this? So it's like, we don't build our phones and our cars in nearly the same way we did 100 years ago, but yet we still build our houses in the same way. So it begs that question, is it time to rethink, or what is it that's causing us to continue building that way? On top of that, we have an interesting issue. Since the financial crisis in 2008, the increase for new homes combined with a shortage of skilled home builders has been driving up construction prices. So even building the same way as we have 150 years, the prices have been going up and up and up since 2008. And we're not building enough homes. In fact, in 2019, we were about 200,000 homes short of fulfilling our need, which is increasing the demand for home builders, while actually young people are not going into the trades as much as they were 10, 15, 20 years ago. So costs of things are going up, and maybe there's a need for rethinking. On top of that, I don't know if any of you noticed, but last year, timber prices, lumber prices, almost quadrupled. They spiked through the roof. We went to Home Depot, and a sheet of plywood that used to cost, $20 was suddenly costing around $90. So suddenly prices going even more through the roof because of this reliance on basically one type of technology, which is lumber. Most of our homes are built with softwood timber or USB plywood, or, we don't have a variety of different things that we're looking at. So here comes the other question. Again, it goes back to that kind of romantic idea of like, oh, the timber is nearby and it's milled at a local thing, but where does your house actually come from? Or maybe we should rephrase that. Where did your house actually grow? And what's interesting is most timber, if you look at this survey that the SUNY College of Environmental Science and Forestry put together, for frame of our house, most of the softwood that we use today actually comes from Canada. And a good chunk of it comes from Chile, Brazil, New Zealand, Germany, and Sweden. For sheathing, OSB, we're getting a lot of it from Europe, Russia, Africa, or the majority of it comes from Canada, Brazil, Chile. And flooring is coming from Canada, China, Sweden, Indonesia, and Brazil. So there's no, in this global economy, there's not this romantic idea anymore, or reality that any of the timber is coming locally. Even think about the project you guys are working on. The timber did come fairly locally where you're working on, but it's not coming locally where it's going to be installed or where it's intended to be installed. In fact, the convention these days is long distance of travel. And if you think about, what is the carbon footprint of that timber that's coming from Germany or from Chile or from New Zealand or even from Canada? It's a very long distance travel. And so actually the one thing that's conventional about the way you guys are building the truss for Notre Dame is in fact that you're prefabbing it on a continent where it's not going to be installed, assuming it gets installed. I know that's a debate. So it's a bit ironic if you think about history. So also there's a question of what climate in the US is your house designed for? Is it designed for the California wildfires that happened or happening this summer and have been happening the last few summers? You know, are the material choices picked to be optimal against fire where that happens frequently? Are they picked to be optimal for the kind of flooding that might happen in Houston? Are they picked to be optimal for the snowfall that might happen or does happen in Colorado? Or the kind of dust storms that happen in Arizona or the desert areas of the Southwest? Well, ironically, I mean, here's a climate map of the US. Huge amounts of differences in climate, but we pretty much build the same way everywhere we go. They're not adapted to the climate. If you want to see a house that is adapted to the climate, you're going to need to live in something like this. This is the Mesa Verde from the 1200s. This is an adaptive design to a local environment. Or something that looks like this. There's a passive house from Plymouth, Massachusetts, Wampanoag Nation. If we lived in things that looked like this, they might actually be adapted to the regional environment using local materials. But we probably live in something that looks a bit more like this, which was designed to be adapted not for this continent, but for this continent or this island over there. And we build that way pretty much ubiquitously all across North America. And the question I would ask is, which climate region is this, material aisle optimized for? Well, you go to pretty much any box store like this, and you're going to find anywhere across the nation, they pretty much have the same supply of materials. So the question I ask is, what is the alternative? What is the future of this? It's already too expensive for us. So can we create a variety of alternative materials? Well, this is something I happen to research in a lot of different ways. One of my favorite ones is, this is a conventional material in Europe. It's a sustainable structural masonry that's actually has very good R values or low U values, depending on you. But it's not in scope for this lecture, so I'm just going to throw it out there and leave it. But I went on a search for timber alternatives. And again, like I said, I really feel that there's a value of looking backwards and looking sideways and looking up and down at different locations and different historical means of construction in order to try to answer questions that we have today. So I flew, this was, 2019, just before, actually, yeah, late 2019, about a couple months before the pandemic hit, and we were still allowed to travel. I hopped on a plane and went down to the Osa Peninsula, Costa Rica, to look at some a permaculture farm, and look at take a bamboo construction class. And so I arrived there in the jungle, next to the beach, where you can watch, whales breaching and see dolphins floating and great. And you're in this location where you see this amazing, bamboo structure. And where does that bamboo come from? Well, you walk over about 100 feet to the bamboo clump. You get out your Sawzall and you trim a couple of those bamboo, and you take about 2 or 3 people who are to carry a 40-foot long piece of timber out of the woods. You treat it by, buying about $800 worth of PVC and plumbing fixtures and a compressor, and you push a salt water mixture with a little bit of borax in it to push out the sugars and fill the fibers with salt water. You stick it in a little shed for a couple months, and then you build some amazing structures, all done within a few hundred feet. Now, I'm lying a little bit. This is Bali. This is not the Costa Rica place, but same principle there. All the timber and all the materials were taken from within a few hundred feet of the location, maybe a few miles. Maybe there was a few little pieces of steel and other members that came from farther away, but a majority of the materials came from locally sourced, very locally sourced, and very low energy processing. So here's just some examples of what bamboo timber can actually produce. And so I was like, very interesting. So in the tradition of Robert Venturi and learning from Las Vegas, I'm thinking, what can we learn from San Jose? Okay, this is great in a tropical environment, but can we learn something from this? I mean, let's actually, on top of it, I pulled the slides here because I was worried my lecture was getting too long. You are even able to go get lunch by pulling a papaya off the tree or picking a pineapple off the ground. I mean, you're in a place where it's a permaculture forest where the food that we were eating was locally grown, the materials that we're building all the things out of was locally grown, and the labor was, okay, came in from St. Louis and from all around the world. But is this something that we could go back to? Because that was that idea from that initial 1800 balloon framing, the idea of that locally grown materials, which we've kind of lost in the shuffle of trying to maintain that convention. So looking at the climate zone map again, and with the hardiness zones, first thing I discovered is that there's actually plenty of species of timber bamboo that could grow in St. Louis. So here's St. Louis, and I'm kind of going to focus on St. Louis here, which is climate zone 6. But you see that is actually climate zone 7, which where you guys are at, is even, probably even more species would grow, because there's like 1,400 different species of this stuff. And what could grow here, could grow up even in New England and, New York and Boston, could grow in a lot of different places. And so, here's a handful of different timber species that could grow there. And I even brought home a chunk. So if you guys can see this is a piece of timber bamboo right here. It's pretty big and round. You can see it's like probably 6+ inches in diameter. It's got a thick wall. It's just a little chunk because I brought it back. But this is actually a species that would grow in St. Louis. It would grow not quite in Boston, but maybe in New York. It definitely grow in DC. This could grow readily. It grows very easily in North Carolina. It can grow all over the US. And what's interesting about bamboo, it's not actually a timber. So I'm kind of lying to you. It's not truly a timber. It's a grass. And, it can grow within a handful of years. You can have a full harvestable bamboo grove in about 4 to 5 years. You plant the rhizomes. They start with these kind of small little bits. And then after 4 or 5 years, the rhizome is established that it will start shooting up full size timber bamboo culms. But what's interesting about bamboo is it grows very differently than we think about timber. A softwood tree starts small and grows its way out. A piece of bamboo actually grows to its, once the rhizome is established after 3 or 4 years and is healthy, it will shoot up a culm in its full diameter and reach its full height in about 3 months. And then what it does is it actually starts to grow inward. So the hard, incredibly high tensile and compressive strength outside is there right from the get-go. And then it grows inward and the inner wall starts to harden over 2 or 3 years. And at about year 4 to 5, you can harvest it and have very strong timbers that are like an optimal shape for a lot of things. I mean, it's round, it's hollow, it's light, it's got all the structure on the outside. It's really kind of an optimized shape for structural struts, for example. Of course, one thing you have to control is how it spreads. There's a whole series of ways of doing that, which I'm not going to go into because I want to move forward. But you see here's a bamboo bud coming out, and you see it comes out in its full diameter and then shoots up in about just a couple months. And, we already import over $250 million worth of bamboo from Asia and South America to build a whole range of products in this country. For fibers, for food, for packaging, for, helmets, for, all these things you see here. We're already importing a lot of it. So there's actually a local market for it already. So it's kind of like this amazing thing. So I was like sitting here, I was like, okay, I'm back in St. Louis. Let me, take a look at how could this actually be something that we could do in the city? I mean, is this an absurdity? Is this just kind of those like pie in the sky, crazy ideas that madmen think about and you just, that really goes nowhere? But what's interesting, so here's St. Louis, the Arch. I'm sure the St. Louis Arch is down here. This is downtown. And one of the interesting things about St. Louis, and this is true of a lot of central state cities that have kind of been declining in population, is here's a vacancy map of St. Louis. All those green dots you see there are vacant lots. There's over 2,500 square feet, or acres, excuse me, not square feet, 2,500 acres of vacant land in St. Louis. And St. Louis has a complex history, and there's some, some environmental racism involved and other racial issues and complex economic problems that go along with it. But you'll see a lot of sites that look like this. And one of the issues is the reason they're vacant is because they're brownfield sites. They can't be built on. They have either had some fuel dumping in the 60s and 70s, so they have lead, or they have some cadmium or copper in them. And so, what do you have to do in order to be buildable on site? Well, we have conventional remediation techniques. What we normally do with a brownfield site is you go and you dig up some toxic soil and you dump that toxic soil somewhere else, which is also a questionable thing, is where are we dumping it and whose property are we dumping it on? And, right now that's not a valuable spot of land, but maybe in the future it is. And then we bring in some new soil. This is the typical way we would remediate a site, which is very expensive. I mean, there's a lot of national funding for this, but it's very, very expensive. And it doesn't necessarily solve the problem. It just kind of pushes it under the rug somewhere else, which is, in the context of some environmental racism, maybe a whole nother topic and for a whole nother lecture. But what we discovered is that bamboo in China, they're doing research that shows that bamboo can actually remediate heavy metals out of sites. So what if we could plant some bamboo in an urban condition, plant the rhizomes, we enjoy a beautiful grove park, we harvest it annually, actually for a sizable profit. According to commercial bamboo farmers in Oregon and Florida, you can make tens of thousands of dollars per acre per year harvesting bamboo. And you're not clear cutting it, you're just harvesting the culms that are a few years old. And then if you want, you can remove it and move it on to the next site and build a house or build something else there, but you've now remediated the site. So we started playing with this idea of like, what if we started taking sites like this, and what would it look like if we put a grove on it? Could this become a fun park? It could be a destination. We started taking locations. This is Grand Boulevards, the key street in St. Louis. And what if we actually grew a bamboo grove and maintained it and managed it and profited from it and remediated the site? Here's another one. Urban farming, urban forestry. Is it something that could be fun, could be interesting, could be productive? And then, thinking about, okay, well, now if we suddenly had this influence of material, well, what would we do with it? I mean, okay, we don't want everything to look like, a Costa Rican tiki hut, where you think you're going to always buy a margarita and hang out and listen to some Jimmy Buffett, right? So, but what could we actually take in an urban condition? Could it become an urban material? So I just took a corner, street corner in St. Louis, and looked at the kind of elements. Now, remember, bamboo is growing in just kind of a round tubular form. You can get different diameters and things depending on species. Well, I'm looking at a lot of tubular structural elements in this image that happen to be made out of steel. What if we just took those benches, which are just basically tubular steel and some bent tubular elements, and what if we took that bench and we made it out of bamboo instead, made of a locally grown material? Rather than a material, which is steel, that's, although a lot of it's recycled, it's basically, the ore is mined in one place and it's moved over here with really high energy. It's converted into material, and then it goes to another location and it's extruded, and then it comes to another location and it's treated, and then it goes to another, it's driving all over the place again. Huge carbon footprint just in transport, let alone the carbon footprint and the energy use in production of the material, or the recycling material for that matter. What about the fencing back there? I mean, none of this stuff is really there to be aesthetically pleasing. So what if we just switched out the fencing to be bamboo, locally grown? How many emissions would we save if we grew it on one side of town, processed it on the other side of town, and installed it, behind supermarkets and next to sports fields, and then, as just like non-aesthetic locations, but really changing the material? What about those lampposts? Can we switch them out for bamboo? Why not? How much carbon could we sequester if we started shifting from tubular steel to tubular grown materials? Take the bus shelter. How many local jobs could we create? How much could we boost the economy in a local sense and bring people back to St. Louis? So could bamboo be a new urban material? I don't know. Maybe, maybe not. Be an interesting one. And this is what, all this stuff that I'm showing you is like really hot off the presses. It's made last week, if not this weekend, because this is exactly the question that I'm posing and trying to put out there. So this is happening as we go. Could it be a conventional material? This is a conventional agricultural structure or storage structure that's over 12,000 of these, at least in 2018, over 12,000 of these were sold in the central state regions alone. It's basically just a steel frame truss with a fabric that goes over it. Could we switch those out for locally or regionally grown bamboo that grows very quickly, that would, can be actually recreated every couple of years? You could create as much bamboo as you need for the structure in a handful of years, or depending on how many acres you're growing, maybe 1 year. Or, could it be a structural material that we're building some sort of, wild, fun geodesic domes or some other structures? Could it be an inspiring material where we're, using it to create shapes and forms that, here's just a shade for a local garden. These are just photos taken from St. Louis, and experimenting with how, if we started playing with this material, how we could start to think differently. How could we add a arrow to our quiver of materials to diversify the amount of, the materials that we can use, as well as regionalize and localize the production of those materials. So here again, I'm showing you some really innovative stuff that's coming out of Bali, huge grid shells, everything you see in that image, with the exception of the concrete pillars here, or concrete foundations. And the floor, of course, is made out of bamboo, locally created and produced and built bamboo. So what's the future of timber? Of course, it's not to say we're going to stop using softwood or hardwood or any of these things, but it's to throw out there, maybe we need to start thinking about a greater use, a broader band of what timber means and what construction means, and how we build the homes we live in, how we build the buildings we live in. And look around, look into history, look at how things were done several hundred years ago in Europe. Look where things are being done now in certain locations. Look at indigenous technologies, look at local adaptations, look at regional ways of producing and growing and engineering and building. So I'll leave it at that. Thank you guys for your attention. Any questions? I would love to hear more about your project going on there and what your impressions are. And but if you have any questions, love to take them. And thank you very much. I don't know if you're talking, Tanya. I can't hear you.
I'm talking now. Oops.
All right.
I wanted to thank you, Wyly. That was amazing and exciting about our potentials. I want to open to students first before any questions?
Quiet bunch. They all want to go hack some wood
Yeah.
with their axes. I don't blame them. I don't.
So one of the first things I was thinking about was the potentials, and thinking about, or at the very end, these things hot off the presses. So what's the next step? Where are you at? You've got any secrets that you can share with us? You have.
Well, I'm approaching this from this like twofold, maybe from both ends of the game. And one of them is I'm really trying to actually grow bamboo in St. Louis. I mean, that's like my goal, and to do it in a community-based and community-sensitive way, where I'm actually trying to identify local farmers that would be interested in creating some sort of profit or not-for-profit business, get the city of St. Louis to hand over a stewardship or a lease and have them grow it, and just start the growth of bamboo to actually get that across. And I'm finding there's a lot of resistance to the idea of bamboo. One of the two big issues are safety, because what people think of bamboo is they think of that kind of brushy stuff that, gets dense packed, and they're worried about people hiding out in it and camping. And then the other big issue that people come up with, and this is why I'm starting to visualize these things, because it's to show that timber bamboo, this is not your neighbor's bamboo that we're talking about. This is a different size, different scale, different whole beast. And the other big issue that people come up with is the invasiveness of it, which again, it's looking at 2,000 years of Japanese bamboo management and how they've had it under control for thousands of years, and trying to get these cells across. The other side I'm trying to bring it in on is actually from a local neighboring university, the Southern Illinois University in Carbondale is a huge Buckminster Fuller archive. That's where I used to teach. So I'm looking at my background, as you've probably noticed, in cell and then some other structures, is lightweight structures, is looking at rethinking Buckminster Fuller from a perspective of bamboo as the material. He came with this idea of like, how much does your building weigh, and making it economically, using geometry to make it economical or sustainable, really ahead of his time. And now I'm thinking of like, well, how, again, asking the question, where does your building grow? And how can we take those principles and put them together to really think about natural materials as an innovative way of re-looking at lightweight structures?
Yeah.
Thank you for the it's really loud, for the presentation. As a practicing architect, do you find that your clients are interested in using materials that are locally sourced as opposed to maybe at the time more economically or cheaper upfront as opposed to having longer longevity? What are your thoughts on that?
Well, I don't think there's necessarily a dichotomy between locally available and longevity of material. That's more just a matter of how you treat it and how you design with it. So you can certainly use locally sourced material. I mean, for example, let's take St. Louis, for example. St. Louis, one of it was actually the wealthiest city in 1905 when the World's Fair was here. And one of its big economic, boons was brick. So everything in St. Louis that was built 100 years ago was built out of brick. And you'll see there's houses that have been, derelict for decades, but are still standing because it was a locally sourced, well-used material. So locally sourced doesn't necessarily mean not durable, but I find with my clients, it depends on a lot of things. And so some of the clients are, like the stadium was a city, and actually there was funding coming from Germany as well. If you're looking like individual clients that are developers doing multifamily housing that's sustainable or affordable, as I was talking about, the impetus is usually driven by if there's some requirement to get LEED certification. So then there's some limitations on the sustainability and the distance that things are traveled. But in general, I think most people are not aware of where the materials come from. And so whether it's locally sourced or not is not even on the map. It comes from Home Depot, or it comes from Lowe's, or it comes from the store. It's kind of like, where is your food coming from? Well, it comes from the supermarket. So it's like, it's the same idea that's not even on the radar necessarily of most clients. And you can talk about it, but it's not always an easy one to get across, because when you talk about it on a project by project basis, there's going to be huge costs associated with that because you don't have an infrastructure in place to support it. And that's the financial shift. So you have to start building up that infrastructure to make it much more cost effective. So if we're going to try to build a house in St. Louis right now using bamboo plywood and bamboo structure and just using that as a thing, it would be very expensive because the bamboo is coming in from Asia and being processed probably in Canada or in California and be transported. So you can buy bamboo plywood. It's just probably double or triple the cost of regular softwood plywood because the infrastructure is not in place. It's not already being locally produced. But it is that's why, as an academic, I can propose these and start to build things up and work on a smaller scale where I'm not tied into having to, my economic finances based off the project. And I can do projects that do address some of these issues as a second thing. But I am noticing in my clients, particularly in Germany, there is a interest in the ideas of sustainability. So introducing locally sourced materials is something that they're amenable to as long as it doesn't, they don't go bankrupt doing it. So that's why the stadium was indeed that. Everything was within a couple 100 miles or kilometers as I was measured there. And so there is an interest, but it's not necessarily, it's client by client. I know it's a long answer for your question, but it's
Great.
not an easy question.
Yeah.
Lorenzo, Mark?
Thank you, Wyly. That was terrific. I'm curious how bamboo weathers. We really think about wood and different species of wood and their weathering properties and, the right shapes and locations for wood. And does bamboo have that kind of complexity? And how does it weather?
Again, it's a matter of treatment and coating, just like wood in that sense. So the main thing you have to do is you do have to fundamentally, if you just take bamboo and you use it, you cut the stalk and you use it untreated, it will only last a couple years because bamboo is like sugar cane. It's full of sugar, and fungus and insects love it. So it will like start rotting, the moment it's somewhat dry, which is why I showed you that. I very briefly showed it, but there was that kind of plumbing equipment they were attaching, which the first thing you have to do as soon as you cut the stalk is replace the sugars with a kind of a salt solution. I mean, in Japan, they actually just use salt water a lot of times. And in certain Asian countries, they'll submerge it. So you have to get the sugars out and replace it with salt. That's the first one. And if you do that with very little maintenance, that building that I showed you, that when I went to the permaculture farm that was there, that was a 25-year-old building. And timber bamboo, it's like wood. It does need, you need to sometimes wipe a little stuff off of it, but it can last very easily in the outside as long as it's not, extremely exposed to the elements. And Costa Rica is very hot and humid too. It can last for decades, just like you would think any softwood. So if you think about a softwood fence or something, maybe it needs some painting or some coating to make it last longer, but even untreated, as long as it's covered, can last decades.
Thank you. Thank you. I had another question completely unrelated, which is you mentioned Japan.
Mm-hmm.
A history or tradition of managing bamboo and probably using it for certain construction purposes. But they also have a very rich tradition of wood structures. I mean, when we think about Japanese architecture, we think of wood. So what is it about the two materials, wood and bamboo, that have given rise to those two traditions? Why does wood dominate? Why is bamboo, not the dominant construction material?
That's a great question. And I honestly don't know enough about my Asian bamboo history to know that. And I think that's definitely a question that needs to be addressed. It's a good one. I think, timber certainly, softwoods, hardwoods, is certainly a more durable material generally. I think, I'm kind of, as I get deeper into it, I'm even not even convinced of that. But I think that's a good question. I'm stumbling with that one, is why bamboo has not taken off even in those traditions. But then again, it has. I mean, it has for a lot of temporary structures and a lot of technical structures. It could be a matter of the fact that a lot of the Japanese joinery that we know about is the fact that you have a solid piece of wood, and so it allows for a whole different way of working. Whereas bamboo is hollow, so it might be about the joinery and the connectivity, which is typically been kind of like stick on stick with some sort of connection. But with different ways of thinking about it, you can create end-to-end joints. If you think about it like we do tubular steel structures, and how do you create the joints, and how do you create the variability of that? Where if we go back to those trusses, where all the joints of how the tube hits tube, each one of those joints is individualized, which is now not an issue. Where initially, if each one of those joints had to be somehow separately produced, that could be a complicated work scenario. So they just maintained it for scaffolding. Or I remember seeing this is in China, huge water wheels made out of bamboo and infrastructural elements made out of bamboo. So I'm not sure that it's not a hugely used material. And that's where you see that the work coming out of Bali is demonstrating it can be very fanciful and very, very amazing and open up new design ideas. It may simply be a matter of the perception of the material, of the idea of that's kind of a cheap, lesser material than the other. And I would compare that, and now that you got me going on a tangent, if it's interesting, in Germany, building out of wood is considered kind of cheap. They build almost everything out of masonry. And proposing a wooden house is like, oh, I don't want to build a wooden house. That's like going to fall down. That's the perception of wood in a certain culture where masonry is predominant. So sometimes we have cultural perceptions of a material that drive how we construct. Whereas, in this country, if we're going to talk about masonry versus wood, we'd be like, oh, that's too expensive. Or we do build it in masonry, but a lot of times it's with a wooden frame and a masonry veneer these days. So the perception of a material often drives the conventions of why we use it. So I'm projecting. I don't know the history of Japan or China enough to really to say, definitively, but it could very well be. It's just that perception of that material is really, oh, that's for infrastructure, that's for scaffolding, that's for temporary, that's for, but if we want to do permanent, then we, the tree is sacred. The tree is the way we've been doing it. And so that has another value that's not necessarily based off the properties of the material. It's based off the cultural significance applied to it. Does that make sense?
I have one more question. We'll see if anyone else has one after. But so we have a lot of, information about how certain materials work together, and we know what happens when we put materials together that we shouldn't. Does bamboo sort of play with others? Does it get along well with other sort of natural materials better than others, or is it higher performing than others in some cases? Is that clear?
Yeah. And again, I'm kind of new on the construction end of this, really looking at at that level. But from what I've seen, it seems to play well with concrete. I've seen it, basically concrete cast in it to stiffen elements that it's 30 years old. I've seen it work with cob and rammed earth that's been 30 years old. I've seen it work with, obviously using steel pins and elements that have been added to it. So I haven't seen anything that raises a red flag that it doesn't play as well as a timber or something else. Yeah, it's a good question. So again, these are all just things I've seen. I don't have any kind of research to back it up other than in just anecdotal and specific buildings that I've looked at, in particular joinery. It works really well with also with fibers. You can lash it, you can pull things to it. It can be pegged just like wooden. You can basically make mortise and tenon. They're not quite the same as mortise and tenons. I find the biggest challenge working it is the fact that it is round. You guys have just spent a week turning round things into square, so it's a little easier to join. So that's the limitation for it. But as far as performance goes, that structural shape is truly optimal. This is what I mean, comparing it to like when we're going to build a big, steel post that's 20 feet tall. Well, we make a hollow round tube because that's the optimal vertical, overhang that we do it, and it grows in exactly that form. And it's the way it grows, as far as structural goes, the outer skin has tensile strength and compressive strength that's comparable to steel and concrete, that outer skin. So it's really truly structurally an amazingly pre-optimized grown material. What's even fun, and this is where you get into fun things. I've seen people that they'll grow it in like either in a curved kind of tube, and that it will grow in that tube, and then after 3 months you can pop the tube off of it and it will hold that shape. Or I've seen people grow it in square shaped profiles that it will grow actually square. And so you see people do pumpkins and things where you can grow it to different shapes. So there's even possibility that we could modify its growth just by putting it into kind of harnesses or forms as it's growing, because it grows soft and pliable and then it gets hard over time. So I'm not quite, I'm getting off on a bit of a tangent, but there's I think a lot of possibility if we take the time to investigate.
Okay, great, thank you. There is one more question. Hold
Yep.
on.
Hi, Wyly. You can't see me.
I can't see you, but I can hear you. Okay, there, I see you now. Hi.
Thanks for your talk. You mentioned that you are doing some research or looking more into Buckminster Fuller and some of his forms and work and what he was thinking about in terms of the geometry of things and you also mentioned geodesic forms and things like that. Could you just speak a little more to that?
Let's see, I might have a model here. So geodesic means a lot more than we conventionally know. This is actually a geodesic sphere. And It's amazing. So there's an archive as I said, in Carbondale that's been closed to the public for probably 30, 40 years. The archivist really kind of locked it down and was, and it's original models that Buckminster Fuller and his team built when he was teaching there. I forget when he was there, in the 60s or 70s. And I've somehow, finagled some access to these things. And I've seen some of these models, which explores the geodesic in ways that if you look at mathematics and the geodesic and you see the different things, it's all there. But it was really looking at the construction. It's looking at these models and how they're constructed. Some of them are soldered metal. Some of them are folded paper. Some of them are, using their half tensegrity based geodesics. And there's suddenly this deep exploration into how this geometry can not only be optimized in its the fact that it allows for very thin shells, but also in how it can be optimized for very simple constructability, very simple joinery, very simple, minimal amounts of materials. And so it's really way ahead of its time. And I did a bunch of research. I did at the Frey Otto Institute of Lightweight Structures in Stuttgart. Was there for 2 years, and so lightweight tensile structurals, tensegrity, grid shells. This is all kind of where I spent a lot of time working. And so what I'm looking at right now, my kind of research project right now is I'm trying to take these 120 so models, and let me see, maybe I even have a quick something I can show you, and analyzing them. Do I have actually? Oh, I don't think it's sitting on my desktop conveniently. No, I can't do that. I'm analyzing them geometrically and then constructively, and then trying to look at how we might design with them on a larger scale. So a lot of these things are just academic exercises, but I'm exploring them as actually design exercises. Because again, his whole thinking was minimize the amount of materials you're using. And now if we combine that with materials that could grow locally and are also optimized for their construction in the way that they actually come out of the ground, maybe there's a marriage of two sustainable ideas that can push us into a whole new way of thinking of construction and of regionalized design. So there should be a forthcoming book in the next couple of years, which I can.
All right, if there's no more questions, thank you, Wyly. Thanks so much for your time and this awesome lecture.
Well, thank you guys. Thank you, Tanya, for inviting me. And thank you all for the amazing work you're doing in DC. I love watching the feed. And I guess you guys are raising it tomorrow. Is that right? Is that still on schedule?
That's right. Tomorrow, the Raising campus. I'm sure it will be smooth with 0 hiccups.
Yeah.
And everything will go down and be disassembled on Wednesday, and then Thursday at the National Mall, and Friday in the Building Museum. So it's exciting.
Very good. Well, thank you guys. Thanks for your questions. Appreciate it. And have a great day swinging some axes.
Thanks, Wyly. See you soon.
See you later.
Bye.